Good evening to all the fellow attendees over here. This is the day 2 of our series in Qiskit Programming, and today we will be having a very special guest between us. So without further ado, I gladly invite our speaker for day 2, Ms. Shilpa Mahato. Good evening, ma'am. Before proceeding, I would like to give a brief introduction of our guest speaker. She is a final year student at IIT Dhanbad doing bachelor's in technology with branch engineering physics. She is an aspiring physicist. Her research interests primarily revolve around quantum computing and quantum information. She has achieved great heights and success. Besides being a student in college, she is an active and valued member of the Qiskit community, serving as an IBM Qiskit advocate. She is also a MIT ACS GRI 2022 Fellow and is currently a summer intern at Wilfrid Laurier University, Waterloo, Canada. So without further ado, I request Shilpa ma'am to take over this session.
Thank you so much, Tina, for the wonderful introduction, and good evening, everyone. So I hope you guys are ready, and I'll try my best to not bore you with a lot of nerdy stuff and make it as interesting for you as possible. So I hope you guys like it. I'll start with the presentation. Can you see it? Can someone confirm?
Yes, ma'am.
Yes.
It's visible.
Okay, thank you so much. All right. Let me just. So, as Dina has already mentioned, that I am an IBM Qiskit advocate. So, maybe some of you are not aware of what IBM Qiskit advocate actually is. So we are just a community of Qiskiters, and it's just a closed circle, and there are a lot of perks of being in this community, which I'll discuss at the end of the session. But for now, that's all, and we can move into introduction to Qiskit. So, okay. So some background about me, although Dina has mentioned a lot, but so here I am, a physics nerd and an experimentalist. As a hobby, I like dancing, and obviously I'm a Qiskitter. That's why I'm here, right? So as already mentioned, I am a MITEX GRI fellow. So under the fellowship, I got to work at the Institute for Quantum Computing at the University of Waterloo. It is one of the leading institutes in quantum computing. And if you are considering to study quantum computing further, you should definitely consider this place. So those are like a few snippets of me standing in front of the Waterloo University. And over here, I'll just get the laser pointer 1 second. Over here is the lab where I'm working right now at my university, and I'm doing some optics experiments. So that's something about me. And we can move further into the talk now. So I have 2 parts of the talk, although it's mostly part 1, and part 2 is where I discuss more about Qiskit as a community. So it's mostly going to be part 1 and a really insignificant part 2. So continuing, so I'm going to discuss about a quantum protocol. I am assuming in the previous talk, you guys already had some introduction to Qiskit, right? Like, you know what a qubit is or a gate is. So I thought I'll discuss about a quantum protocol So there are like so many of them, and I chose something which I personally love the most and is the easiest and also the most interesting protocol you could relate to. But I have some suspense, like you have to guess what exactly I'm going to talk about. Before that, let's have a checklist. I hope you know linear algebra. I hope you know quantum states. I hope you know what a qubit is, what is superposition, entanglement, quantum gates, the single qubit gates, the multi-qubit gates, and basically just enough information so that you know how to construct a quantum circuit. So moving further, I have a question for you. So I have a picture here, and can any of you guess what it is? Anything. It's a machine. I'm gonna give you a hint, and I can give you a second hint, but let's see if you can get the guess right. So would anybody like to volunteer? Anyone? I mean, you can just put it in the chat if you're too shy to speak. Okay. Okay, no idea. But that does look like a cool machine, right? So your second hint is this doesn't really exist and it's a snippet of a movie. Uh, does it ring any bells? Can anyone guess it? No, it's not a quantum computer.
Maybe some kind of teleporter or something.
Yes, that's right. So this is a transporter from the Star Trek. So what is a transporter? It's basically a teleportation device that they portrayed in the movie. So from there, I'm going to talk about quantum teleportation. So what is teleportation? So scientifically, when we talk about teleportation, it means like we have, for example, an object, or let's consider I'm here and you guys are based in Kolkata, I assume. So what if I want to teleport to Kolkata right now? So what happens is that when you teleport an object, basically the object in, for example, we have two places A and B, and you're teleporting the object from place A to place B. What happens, basically the concept is the object gets destroyed at place A and a new copy of the object gets created in place B. I have a wonderful animation over here. So there's my favorite animal, cat, getting teleported from this place to this, from one place to another. So this is the basic idea behind teleportation, but we cannot really teleport, right? But I wish we could. But quantum teleportation is actually a real thing. Like teleportation actually takes place. But when we talk about quantum teleportation, it usually involves photons. And it's not like the photons are being teleported from one place to another. Rather, it's information which is getting teleported from one place to another. So what exactly I'm talking about will be more clear. So quantum teleportation, it forms like the basis for quantum communication. So its application lies in designing quantum communication channels. Basically, what happens is information at one place is destroyed, and the same information is created at a different place. So in a way, you can say that the information got teleported from one place to another. So that is what communication is, right? And this takes place via the means of entangled photons. So basically, quantum teleportation is the basis for quantum communication. That's what I'm talking about. Now, understanding quantum teleportation. Here comes the bad mathematics part. but I will explain this more briefly, like in more details to you soon. But just get the basic idea. So we have two parties, okay? We have Alice, this person, and we have Bob. And they have this connection, some sort of connection between them. This is basically a quantum channel they are sharing. And they are going to transport information through this channel. If you are familiar with the linear algebra, which is very basic for quantum computing, and even if you're not, just try to get the thing. So psi dash over here is a random quantum state. So I hope you're familiar with quantum state, so you understand that this is a random quantum state. And phi plus this is also another quantum state. And this is one of the Bell states. There are 4 Bell states. And this is one of them. And this Bell state has been used as a quantum channel between Alice and Bob. Now, so what is going to happen in the quantum teleportation protocol is this random state is basically the information that Alice needs to send to Bob. Now, what you can say is that Alice could simply like copy the state and send it to Bob, but there is something called no cloning theorem in quantum mechanics, which means that if you have a quantum state, you cannot create an exact copy of that quantum state. So now if Alice is located somewhere, let's say Bob is located in Kolkata and Alice is located, say, in Dhanbad, how is Alice going to transport this state to Bob? So there she is going to use quantum teleportation. And I'll go more into details about how exactly this is working. But first, I will tell you the protocol for quantum teleportation. So as you can see, there's a third party who is 𝓠ᴜ. And 𝓠ᴜ is the manufacturer of the quantum channel. So 𝓠ᴜ basically creates entangled qubits and shares this qubit with Alice and Bob. Now these entangled qubits is basically this state. If you know quantum entanglement, you know that these states are entangled, right? So once 𝓠ᴜ has created this state, he's going to share it between Alice and Bob. So the subscript, you notice, this qubit lies with Alice, both this one as well as this one. And the subscript B is for Bob. So the second qubit lies with Bob. Now, once 𝓠ᴜ has created the entangled qubits and shared it between Alice and Bob, now it's Alice's turn to teleport the qubit, right? So what Alice does is, Alice has the random qubit, which she entangles. She performs some kind of operation between this state and her qubits, and she entangles the random qubit with the quantum channel. And once she has done that, she performs some measurement. I'm giving a very basic overview, so even if you don't understand, it's okay. She performs some measurement and shares the results with Bob. And depending upon what communication she has with Bob, Bob has to perform certain operations on his end to actually receive the original Alice's qubit. Maybe that's a lot of jargon for now. I am going to explain everything on pen and paper soon. So before that, I'd just like to say here, no qubits are actually being sent. It's just we are imagining that they are being sent. And this part will be more clearer later on, hopefully. So this is the quantum teleportation circuit. And I hope you know what a Hadamard gate is, what a CNOT gate is, and what is quantum measurement. And if you know it, you'll understand what exactly the circuit is doing. I'm going to give you some reference about what these qubits represent. So Q0 is the random quantum state which Alice has, and she needs to send it to Bob. Q1 and Q2 are the entangled states that is shared between Alice and Bob. Here, Q1 state is with Alice, and Q2 state is with Bob. CRZ, CRX, these two are the classical registers, and these three are the quantum registers. So step 1 of the protocol is Telemann creates an entangled state. So it's a bell pair. Now, how can you create a bell pair? Basically, you apply Hadamard gate to any one of the states, and then you apply a CNOT gate. Now, depending upon whether it is 0, 0, 0, 1, 1, 0, 1, 1, whatever is the value of Q1, Q2, you can get one of the 4 bell states. So over here, this is going to create the bell state I have written over here. So once the bell state is created, a quantum channel is established between Alice and Bob. Now, step 2 is Alice needs to perform her gates, her sum operations, such that the random qubit which she possesses and she needs to send to Bob entangles with the quantum channel. So what she does is perform a CNOT gate and a Hadamard gate. And the meaning of this operation you can understand is that she has the random qubit and she is a part of the quantum channel. And what she is doing is taking the random qubit and entangling it or connecting it to the quantum channel. And the next part is she now performs a measurement. This measurement is performed in the Bell's basis. When I say Bell's basis, it means that the resultant is like in one of the Bell spaces. I'll explain it more mathematically. So what you understand is that after Alice has entangled her random qubit to the quantum channel shared between Alice and Bob, she performs some measurement on her qubits. So over here, Q0 and Q1 are Alice's qubits. So she performs a measurement and she gets some result. And then she shares this result with Bob over a classical channel. So Alice just calls Bob up and says, okay, I got the third Bell state. So now Bob knows that Alice's measurement result is the third Bell state. So he has to perform, there is already a set of instructions which has been shared between them, what operation Bob needs to perform in order to retrieve the original state. So I'll move on to the next slide. So it's like so over here, as you can see, Alice is measuring her state and she is going to receive, she is going to get some measurement results. So if this measurement result is 0, 0, Bob needs to apply this gate. This is the identity gate. If the result is 0, 1, he needs to apply the X gate. And if the bit, the bits received is 1, 0, Z gate, otherwise 1, 1 is DX. So what does this mean? So Alice first entangles her qubit, the random qubit she has, with the quantum channel, and then she performs a measurement. And then depending upon the results, she calls Bob up and gives the results. So this is the information that Alice shares with Bob. So it can be either of these 4 possibilities, okay? This is either of them, it's not like all of them. So let's say Alice calls Bob up and says like, okay, so my measurement result is 0, 1. So now Bob knows that he has to apply X gate to his qubit, that is qubit Q2. And once he has applied that, he will receive the original qubit that Alice was supposed to send to Bob. So does it make any sense? When I say, so basically this is like a code language between Alice and Bob, and this is like already shared template. So Bob knows what operation to perform. depending upon whatever measurement results that Alice has obtained. So this is the very basic of quantum teleportation. This is how the protocol looks like. And we are going to do this in Qiskit. Before that, I would also like to show you mathematically how this is actually working. So for that, I need a second because I'll be connecting my iPad. So just give me one moment. Can someone confirm if you can see my screen?
Yes, yes.
Yes, yes, yeah, sure.
All right. Thank you. So, yep. I am not sure if I can hide this, but let's just slide it to the corner for the moment. I have the circuit for your reference over here. So if you remember correctly, just give me another second. So the random state that we took into consideration psi dash was alpha 0 plus beta 1. Okay. This is any random qubit, what a random qubit looks like, right? And the quantum channel that I took into consideration, phi plus, is this one. Cool. If you remember well, so this is the quantum channel. Please pardon my handwriting. And this is the random qubit, which requires to be teleported from Alice to Bob. So let me test your memory. So what was step one, if someone can walk me through? Anyone? All right. So step one was of the protocol was creating the Bell pair, which is going to be the quantum channel. So over here, you can assume it's already been created. So this is the Bell pair or the Bell state to be used as the quantum channel. And this step is done. So for your reference, I'm also going to put the subscript here. This is Alice, this is Alice, 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 Bob, Bob. It simply means that this qubit is, one second, simply means that this qubit is with Alice and this one is with Bob. Okay. So step two, if you remember correctly, was Alice performing some operations on her qubits. So she basically entangles the random qubit with the quantum channel. Okay. So wait, before I go through this, I am going to write the combined state. So now the combined state is psi dash. This is tensor product. So if you do this, what we are going to get is something like alpha 0, 0, 0 plus alpha 0, 1, 1 plus beta 1, 0, 0 plus beta 1, 1, 1. This is nothing. This is just combining this state and this state together. Now, coming to step 2. So step 2, if we go to the circuit, so even over here, I'm going to, okay, I am not able to edit the image. Oops. So if you look into the circuit, what are the operations performed? There's a Hadamard gate and there's a CNOT gate, right? So that is what we are going to do. So we have to perform Hadamard gate on the first qubit and a CNOT gate on the from first to second qubit. So remember the chronology of the operations. See, first we have to perform CNOT gate and then there's the Hadamard gate. So in linear algebra, when we are writing, so we write the gate we need to perform first towards the right. And then it's like the chronology is from right to left. So first there's going to be the CNOT gate and then there's going to be the Hadamard gate, okay? And this we are going to perform on this state, okay? On this state. So this is psi dash. So moving on, what will be the resultant? I'll just write one step down. So we have this state. I'm just going to copy this quantum state. Okay. All right. So, okay, that just got blocked, but never mind. Performing these operations. So first I have to perform the CNOT operation. So identity, so CNOT is a 2-qubit gate, right? So CNOT is from 1 to 2, okay? And identity gate is on the 3rd qubit. So basically we change nothing for the 3rd qubit and we perform a CNOT between the 1st and the 2nd qubit. So I'll show you the results of the first two. So we have alpha 0, 0, 0, 0 state, right? So the third 0 is gonna remain as it is. So 0, 0. So 0 is the control qubit. And so if it is 0, then there is no change on the 2nd qubit, right? That is what CNOT gate is. So we have 0, 0. Next, I'm going to leave this blank. Then we have beta. This one, 3rd qubit is as it is. And so we have 1, 0. 1 is the control qubit. So when 1 is the control qubit, we know that the 2nd qubit is going to flip, right? So that is 1, 1 plus beta. I'm going to leave this blank as well. The state is 1, 1, 1. Just going to write it here. So yeah, I'll give you like a quick 2 minutes. Just tell me what is this state and what is this state. This is just for me to know that you are getting what I am writing over here. And yeah, just put it in the chat box. It's really easy. I'm just doing a CNOT gate between the first 2 qubits and the 3rd qubit is as it is. A quick countdown. So it's 12 right now. Is anyone gonna try? Okay, I'm gonna tell you the answer for this one, but the third one you have to try on your own. So what do we have over here? Let's write it in red, okay. So we have 0, 1, 1, okay. I said keep the third qubit as it is because we are applying identity operation. And then we have C0 gate between 1 and 2, right? So first qubit is the control qubit. So 0 is the control, but it's 0. So there is not going to be any change in the second qubit. So it's 0, 1, that is as it is. So we have alpha 0, 1, 1. Is anyone gonna try the last one? You can guess, it's just 3 qubits, right? It's just 0 and a string of 0 and 1. Anyone? 1, 0, 1. Yeah, that's correct. It is 1, 0, 1. So we have, so yeah, cool. Now I know you're getting it. So awesome. We have applied C0 cross I. Now we have to do Hadamard gate on the first qubit and identity gates on the second and third qubits. So I hope you remember Hadamard of 0 is 0 plus 1 under root 2 and Hadamard of 1 is 0 minus 1 under root 2. So we just have to perform Hadamard on the first qubit. So what is it going to look like? So I'm just going to show you for the first one. So we have Hadamard. So we already have a 1 by root 2 outside. And we have to do a Hadamard on alpha 0, 0, 0. So alpha is just the phase. So we have alpha by root 2. And then it is, so if you know, well, 0, 0, 0 is nothing but 0 tensor product 0 tensor product 0, right? So this is the state, and I am actually applying H tensor product I on this. I'm applying on alpha by root 2. Just forget alpha by root 2 for the moment, and let's keep it outside. And I'm applying this on the state. So what is going to be the resultant? I'm just going into the details because I want you to understand what I'm writing. If you know, it's good. So Hadamard is applied on the first qubit. So we have 0. So Hadamard of 0 is this one, right? So this is simply 0 plus 1 by root 2. And this, then we have the identity gate. So it's going to be 0. And then again, identity gate. So it's going to be 0. So what's the resultant state? So we have alpha by 2 outside. So we have 0, 0, 0 plus 1, 0, 0. Does it make sense? So if you do this for all the four states, we are going to be left with something like alpha, half alpha, 0, 0, 0 plus 0, 1, 1 plus 1, 0, 0 plus 1, 1, 1, and plus we have beta 0, 1, 0 plus 0, 0, 1 minus 1, 1, 0 minus 1, 1, 0, 1. Okay, this is going to be the final state after Alice's operation, okay? Now this can be written as, you just need to take a few common out and you will see you can write it as 0, 0, alpha 0 plus beta 1 plus 0, 1, alpha 1 plus beta 0 plus 1, 0, alpha 0 minus beta 1. And we have the final 1 plus 1, 1, alpha 1 minus beta 0. Awesome. That took me a really long while to write. But this is the final state that Alice is left with after she has entangled, after the step 2, okay? Now, what step 3 is, Alice needs to perform measurement. So she is going to do a measurement, and depending upon the measurement results, she is going to tell the measurement results to Bob, and depending upon those results, Bob is going to perform some operations. Now, if Alice measures in the standard 2-qubit basis, that is 0, 0, 0, 1, 1, 0, 1, 1, she is going to get either of these 4 results. So let's say Alice performs her measurement and she gets the result. As 0, 1. So if you know, well, whenever a measurement is performed in quantum mechanics, it collapses the state, okay? So the moment Alice measures and the result is like 0, 1, I'll write it nicely. The other part of the quantum state is alpha 1 plus beta 0. That is the state. Similarly, if let's say Alice's results is 0, 0. So what is the quantum state collapse to? It is alpha 0 plus beta 1. Now, if you have understood this much, you have understood the protocol, okay? Because step 4 is nothing. Now, Alice basically calls Bob up and says, hey, I received my measurement results is 1, 0. Now, Bob has this list, okay? So if it is 0, 0, he performs nothing, or an identity gate. If it's 0, 1, he performs an X gate. If it is 1, 0, he performs a Z gate. And if it is 1, 1, he performs a Z gate and then an X gate, okay? So Alice calls Bob up and says, okay, I have 1, 0. I have my measurement results as 1, 0. So 1, 0, can you tell me it corresponds to which of the state? As in, what is the quantum state right now? So it is the third one, okay? So here it is 1, 0. So it means Bob has this state with him. Okay. So this state is with Bob right now. Now Bob has received the information 1, 0. So 1, 0 is this. So now he needs to perform Z gate to retry the original quantum state. So Bob is going to do Z alpha 0 minus beta 1. And if you know the basic gates, Z gate on 0 gives 0 and Z gate on 1 gives minus 1, right? So we have plus beta 1. And guess what? Which state is this? Isn't it the state Alice wanted to teleport to Bob? Isn't this the state? And now Bob has it and he didn't even know how he received it. So that is what is the quantum teleportation protocol all about. And I would like to clear out again which qubit belong to whom. So over here, I forgot to mention. So the first two are Alice's qubit, as always. The third qubit belongs to Bob. Okay. And in this resultant state, again, the first two are Alice's qubit. And these are Bob's qubit. So when I say these are Bob's qubit, Bob has only access to these qubits, and he doesn't know anything about Alice's qubits. So Alice has to share the result in order for Bob to know what his future operations are going to be. So I guess I have somewhat made sense about what this protocol is trying to do. Now we are trying to do this in Qiskit. I'm going to show you how to run the quantum teleportation protocol in the Qiskit. So I'll again go back to my computer. Just another second. Okay. All right. So before the talk, I decided to write the code up, and I'm going to share it with you guys. And can you see the IBM Quantum Lab window? Can someone confirm?
Yes, it's visible, right?
Okay, awesome. Cool. So these are basic import that we need to do. So I have, you can just import the entire Qiskit, but it takes a lot of time to load. So I have the things that I need. Now, setting up the quantum circuit. If you know, so quantum resistor is, so we need 3 quantum resistors for this protocol, and we have 2 classical resistors, if you remember from the circuit. So we are creating the teleportation circuit. So it has the 3 quantum resistors and the 2 classical resistors. So step 1, so now this is the 3rd time we are discussing the protocol. Step 1 was Telemann creating the entangled pair of qubits, giving one to Bob and one to Alice. So I have defined a function creating the bell pair. So first there's the Hadamard gate and there's the C0 gate. So we perform this function on our teleportation circuit, and I have drawn the circuit. So this part of the circuit just creates the bell state and is shared between Alice and Bob. So once again, I'd like to repeat, Q0 is with Alice, Q1 is with Alice, Q2 is with Bob, okay? And CRZ and CRX, the one wherever there's a double line, so these are the classical registers. Now, Alice, step 2 was Alice doing some gate operations to connect her the random qubit with the quantum channel. So she applies a C0 gate first to Q1, controlled by Q0, and then she applies a Hadamard gate to Q0. So when I say psi, which is the random state, okay, this is Q0, okay. So we have defined Alice's gates, and this is a function I have defined, and then I do the step 2 is Alice performing her gate operations. Again, as you can see, the circuit over here. So this part of the circuit was Telemann making the entangle. So when I say Telemann, it's not really Telemann. So it is between Alice and Bob only. So it's just I'm referring to a third party right now. So they have created an entangled bell pair. And this is the Alice's gate operations. Next, Alice does is perform measurement on both her qubits. So Q0 and Q1 are Alice's qubits, okay? And she performs measurement on Q0 and Q1, and she stores this result in these two classical bits. So as you can see, these are the measurement operators, and she stores this information in these two classical registers. Now, Bob already has Q2, the qubit 2, right? So now what Alice does is, when I say she calls Bob up to tell the measurement results, but in this quantum circuit, actually she can't call, right? So we'll see how it has been implemented. But this is the basically the list of operation that Bob needs to perform, conditional operation. I have missed out the gates over here, but this is basically X, Z, and ZX. We just saw what operations Bob needs to perform. So depending upon the measurement results, that is whether it is 0, 0, 0, 1, 1, 0, 1, 1, this is, I have defined a function where Bob needs to perform like these operations to retrieve the original state, okay? Now, this completes the circuit, and this is the complete quantum teleportation circuit, as you can see. And I have put all these steps in one place. So this is going to define the entire quantum teleportation circuit. So as you can see, it's not very big, and you can do it in your computer as well right now. And I do have an exercise for you. You can try it out. So this is the circuit, right? So we wrote the protocol, but how do we test the protocol? Like, how do you even know it's working? Like, I can just write anything in the quantum lab, get it running, but how do you know that it's actually teleporting a random state? So I am going to show you a simulation. So you can simulate this protocol in the simulators available. You can also do it in the IBM quantum system. Unfortunately, I couldn't do it right away because I didn't have the time to like run the entire code. So, but I can show you how it's done as well. First, we can try out with the simulator and see if it is working, right? So again, we have the import functions. And so first, our first step is now to create a random state, okay? And this we can do by using a random state vector. So this is going to result a very random state anywhere in the block sphere. I hope you're familiar with a block sphere. I'm guessing this is something that has been covered in the first talk. So this is a block sphere. And as you can see, any quantum state is represented on the surface of the block sphere, any pure quantum state. So I have called this function and I have got this very, very random state. And this is the representation in the block sphere, okay? So what we are going to do is take this state and we are going to teleport this state to Bob. And let's see if it actually works. So we have something called initialization instruction. Basically, what it does is, so whenever you're working with quantum circuits in the IBM quantum lab, all the qubits that you consider, they are always like initialized to 0. So if you want to change the initial state to some other state, you can use the initialize function. So we have psi. This is the random state that we have obtained and we are going to teleport it. So we are using this operation to initialize the qubit Q0 as psi, okay? Even though it's written init gate, I want you to understand it's not really a gate operation. it's just an instruction and not really a gate operation. This is important to understand because gate operations in quantum computers are reversible in nature, and this instruction is not reversible. So this is just a function to initialize the first qubit to psi, okay? Then I have put the definitions that we have used for the 4 steps, that is Bell-Pierre creation, Alice gates, measurements, and Bob's gates. So this is the quantum teleportation protocol, okay? So first we create the quantum circuit, and then we initialize the first qubit, and then the steps are same, okay? So it just has one extra step, the step 0, and all other steps are same. And this is how the circuit looks like. Now we are going to simulate this. So we have called the AR simulator, and we have plotted the block multivector for the qubits. So we have 3 qubits, 0, 1, 2. If you remember correctly, qubit 2 is the Bob's qubit and is supposed to represent the teleported qubit, right? So when this measurement is performed, basically, and after Bob's gates, you'll see that qubit 2 is always the same because this is the qubit which has been teleported from Alice to Bob. The measurement results of qubit 0 and qubit 1 could be anything. You can run this code like multiple times, and this could be either 0, 0, 0, 1, 1, 0, 1, 1, any of those. But qubit 2 is always going to be this vector. And if you know which one this is same as psi, that is the state that we are trying to teleport. So I will give you 1 second to look at and compare, are they indeed the same? So this is the state we wanted to teleport, and this is the state which is with Bob, which has been teleported. I think they look kind of same. You can tell me if they don't, but obviously we're not going to look at the states in a block vector and compare and say that they are same, right? There must be a way to check. Of course there is, but according to your opinion, what do you think? Is qubit 2 the same as psi? Maybe in the chats. So this is psi and this is qubit 2. I think it does look same, right? Now, what's a way we can check it? So remember when I said like we were performing this initialization operation, I said that it's not really reversible, right? So we can do something called an inverse initialize. So what is it gonna do is just inverse all the operations such that like if I have psi with me, it's gonna inverse the operations and I'm going to get 0 back. So initially I had 0 and I use the initialize function to initialize it to psi. And now I'm saying that I have another function which is going to reverse the initialize operation. And so if I have psi and if I put it as an argument in the reverse initialize operation, we are going to get 0 back, right? So that is what I have defined over here. So there's something called inverse init gate. So what it does is basically uncomputes the init gate function. So how exactly are we going to use this? Now, the thing is, we can't obviously see from the block multivector that this is indeed the state that has been teleported, right? But what if we apply the inverse init gate to this qubit? So if we apply this inverse init gate to psi, we are going to get 0 state back, right? So try to understand this. We have 0. We applied the init gate, we get psi. Then we have psi, and then we apply the inverse init gate, we get 0. Similarly, if indeed qubit 2 is psi, if we apply inverse init gate to qubit 2, are we supposed to get 0? Yes, we are. So that is something we can do to check whether or not the teleportation has actually taken place, okay? So I have done this, and as you can see, I have added this gate, the inverse init gate. And then if you see the results, the result over here, I have not put the histogram results here. I think I'll try do that, but what it results is 0. So what it means is that qubit 2 is indeed the teleported, the size state which has been teleported from qubit 0 to qubit 2. So this is one way you can test it. Another way you can test it is that you can plot the histogram, and you can see that by 100% probability, you'll always get a 0 for qubit 2 if you do the inverse init gate. Now, this is the simulation, so it's like 100% perfect. Will you get the same results if you do it in the, say, let's say in one of the quantum computers? So of course not. Like, it will be something like 80-90% as 0 and 10-12 as 1. But mostly you will see that the qubit 2 will result in 0. So proving that the teleportation has indeed taken place. Okay. So I do have, I'm going to stop sharing for a moment. I'm going to share the code for the simulation with you guys, and you can try it out in your own computer. I think that way you'll have a better understanding of, so it's, I have sent it. So yeah, you guys must have received it. So it's a Python file. You can open it in your computer if you have Qiskit installed. And if not, you can always go to the IBM Quantum Lab. And if you don't have an account yet, you can create an account there and just run this code, and you'll see how like you can actually start with any state. Like I have started with a random state. You can start with 1, 0, or any state that you have in your mind. And you'll still end up with the same state after the teleportation, like after you have run the entire circuit. So that is pretty much it. I wanted to talk about, just give me a second. About the quantum teleportation protocol. I am going to go back to my presentation. Okay. So just to go through it again, I hope you understood how I'm creating the entangled pair here, how Alice is doing her gate operations, how she's doing her measurement and she's sharing it with Bob, and then how Bob is performing his respective gates to obtain the teleported state. So that's pretty much it. I wanted to talk about teleportation. And if it was a lot for you, I hope this helps to clear up your mind. And part 2 of the talk that I wanted to talk about is you guys joining Qiskit. And it's like, it's an open community, and there are several ways you can contribute. And I think when you join the community, you also get a lot of chance to grow, understand, and like, you can be more involved. So I would recommend everyone to like take part in the IBM quantum challenges. We have these quarterly. In a year, we do have like 3-4 quantum challenges. There are Qiskit summer schools. That's like one wonderful place to learn about Qiskit. And then there are open source contributions, which are always welcome in Qiskit. You can just go to the GitHub repository and check out how you can contribute to Qiskit. Also, yeah, become a Qiskit advocate. I mean, I think that's the best thing you can do. And maybe you're the one giving a talk next time. So yeah, I'll request you guys to get connected. If you're not on the Slack, Qiskit Slack, join ASAP, because there are so many opportunities out there. And that's it. if you guys have questions, I would love to answer them. And I hope you guys got like something, if nothing, at least you guys got interested into quantum teleportation, because like for sure it does sound really cool, I hope. And I hope you'll read up on it. And yeah, please, I'd love to take some questions now, if you guys have any.
Yes, anyone having any doubt can ask directly to ma'am, or they can write it in chat so I can convey it to ma'am.
Okay, I have got one question in direct message. So I'll just read out the question. That is okay, right, Dina?
Yeah, sure.
Yeah, okay. So how to start with quantum computing as a first-year student? The domain I'm currently working in is medical image processing. Okay. I mean, see, for me, how I started out was like through Qiskit only. If you check out, there's a Qiskit textbook available online, and it has like huge material which covers like everything from the very basics to like the complex algorithms. That is something you can start studying. And like apart from like studying considered, what you can do is get involved in the community. Okay, so there are so many summer schools happening in quantum computing all throughout the year. I will name a few over here so you can check out. Of course, please check out Qiskit events. It has list of so many talks happening all over the year. So Qiskit events. Then there is QWorld. They also have a lot of short courses, and all these courses are like free of cost. Something that I started out with was the Qubit by Qubit course by the coding school. And I think the applications are still open and you can apply. And again, it's free of cost. Okay. So these are some places where you can check out. Also, apart from that, like you will find several Qiskit communities online. There are so many Discord channels, but I would advise like if you join just one, also like please join the Qiskit Slack. So many of your questions can get answered over here. Yeah, I think this is a really good place to start. Like start with any of the courses, you create connections, and you will know what to do next on your own. And also, like as you said, you are working on medical image processing. That's really good. Like there are applications of quantum computing in image processing as well. So maybe you can find something which links both. Um, I hope I answered your question. Anything else? Any other questions?
Sorry to interrupt you, ma'am. I have one announcement to make.
Sure.
There's a attendance link posted in your chat. Please check it out and fill the form likewise. Yeah. Thank you.
Okay. So I'd love to answer more questions. Doesn't have to be related exactly on my talk, but you can ask me general questions about quantum computing, internships, etc. And I'd love to answer them.
I have a one like question about this program. Like, what internship opportunities can a Qiskit advocate get, and what are the future scopes and perks?
Okay. So basically, you don't get like IBM has their internship programs. Okay.
Okay.
A quantum internship program. So what, like if you are a Qiskit advocate, you get an added edge over others, because you are already an advocate, you can write it, you can mention it there, or basically it's a closed community, so it's like a place for connection building. So right now there are like 500 people around the world who are a part of this community. And as a perks, what we get is we get to participate, like we get early access to the quantum challenges that happen. Apart from that, there are several events that are happening where you get called for, and it's all sponsored. And learning opportunity wise, you can get access to a lot of systems which are not open to the public, and you can just be closer to the company, I would say, and that your, like, whatever you say, whatever you do, it matters. But also, very importantly, I forgot to mention, they have mentorship programs which are only open to like the Qiskit advocates. So you get like, you're like top selected to work on some projects, so that is a perk, I would say. And also, as I said, for internships, you get like an added advantage, like you are considered more, I would say, for a position than non-advocates. So yeah, I'd like recommend everyone to apply for this position. Apparently there are like maximum number of like people from India in the community, and it's like growing every year. So yeah, make sure you submit your applications, and I hope you get selected as an advocate. Yep, that's it. Also, yeah, I would share my email ID and my LinkedIn to everyone, so that you can reach out to me anytime you want, and hopefully I can answer your questions. Just give me a second, I don't have it handy. Yeah, and also, yeah, any other questions? So that's my LinkedIn, and you can email me here. Real life applications. Are you talking about quantum teleportation or quantum computing as a whole? Like, because quantum computing does have a lot of application of quantum computing. Yeah, it does have a lot of real life applications, and but it's still, a lot of it is in a research stage, and most of the work that has actually accomplished something, they have both like a mix of classical and quantum computing. And it's like a lot. For example, as we are talking about teleportation in quantum communication, quantum key distribution has actually been used uh, for satellite communication. If you read up, I think the last China's Mars mission, they use quantum key distribution for satellite communication. So application wise, it does have a lot of application. Also, one major application that is also growing is application of quantum computing in finance. And they have like wonderful application in operation research. So that is also one growing field. So, and also there's like
I guess we
So I think I was answering another question. Someone asked me what are the prerequisites for applying for a Qiskit advocate. So basically what you need to show, like they have this application, like a form you need to fill up. What you need to like quantum computing in general. So what you can show is you can start by making open source contributions to the Qiskit GitHub, and also you can be part of community events, like you can mentor summer schools or challenges, or you can write blogs, you can take part in their events, and all of these counts, and you can use this like in your application to show that you have been connected to the community. That is something that you need for the application. Apart from that, there is an exam that you need to take part, like you need to give. It's the IBM Quantum Developer Certification exam. I am not sure about the name. You need to take the exam, and like they have certain minimum scores you need to score. That is all, like the two things that you need for the application. And if you have like contributed significantly and have been active in the community, you're good to go, and you're most likely going to get selected.
Didi, for events, like which platforms we should search for?
Just like for Qiskit, you can just search, like go to the Qiskit website, and there is a tab for events. You can click that. Otherwise, I would say I wrote Q World, right? Just Google Q World, and they will give you an option to connect on Discord. Go there, get connected, and over there, like people keep sharing opportunities. They have lots of channels, so you can get like from one place to another through, like you can start with one. I would say first join the Qiskit Slack mandatorily, and second join the Discord server of Q World. I think these two are the places where you can start, and then you get directed to other places through these. And there are a lot of opportunities, like internship opportunities, summer schools, and hackathons are shared on these platforms. Another platform that you can join is the Unitary Hack. I forgot to talk about this. This is also another great place. Again, you can just Google it up, and you'll find their website, and there will be a place where you can join their Discord server. You can do that, and yeah. So it's just a bunch of Discord servers, I would say, and that would like make you connected to the community, which is like growing very rapidly right now, and I'm sure you'll find opportunities there.
Okay, thank you, Didi.
Anything else? If you guys have nothing else to ask, I think we can wrap up, Tina.
Yeah, yes. So it was a very enlightening session for all, ma'am. I'm sure the attendees will be benefited by this session. So it was nice having you, and in the future endeavors, we wish a best of luck to you.
Thank you so much. It was likewise. I enjoyed as well. And I wish you guys all the luck. And
Yeah.
feel free to reach out to me over email or LinkedIn. And I'll definitely try to help you out as much as I can. Okay.
Yes. Yeah, sure.
All right. Thank you so much. Bye-bye. Good night, everyone.
So this meeting is officially ended. So everyone, I guess, everyone has filled the attendance form.